StockX up 4.2% in 90 seconds. Pattern match, 87%, buying 10,000 shares.
Signal received, routing order filled, increasing position size.
Volatility threshold exceeded. Recommend halt.
Acknowledged. Continuing anyway.
This is not science fiction. This is what happens when AI agents interact in financial markets and poor coordination lets mistakes amplify. Hey, I'm Jacob Marcus, and I work at Meta as a finance manager and mentor students at Interview Kickstart. Today, we're talking about what happens when AI agents don't just act alone, they interact in real time in high-stakes environments. We'll use finance as our test bed because microseconds matter and errors cost real money. But the architecture patterns we cover, agent communication, coordination failures, guardrail design, these show up everywhere. Payments, logistics, healthcare, infrastructure. The reason finance is such a useful lens is that it punishes bad design immediately. There's no, we'll fix it in the next sprint. So 3 reasons finance is the perfect stress test for multi-agent systems. Speed, because HFT systems run at microsecond latencies. Human traders are completely out of the loop. Decisions are made and executed before you finish blinking. Every component in the stack has to be designed with that constraint in mind. Volume is the second piece. Major exchanges handle millions of transactions per second. One bad agent doesn't fail quietly, it scales. You're not debugging one bad trade, you're debugging 40,000 of them that happen in the same second. And the third piece is consequence. The 2010 flash crash erased nearly $1 trillion in market value in 36 minutes. HFT algorithms created feedback loops with each agent responding to what the other agents were doing, amplifying the signal until the whole market briefly went haywire. That's not a coding bug, that's an emergent system behavior, and it's exactly what we need to design against. In Interview Kickstart's Agentic AI program, building a multi-agent financial system is one of the top capstone projects. If you want to check out the program, the best way is to come to the free webinar, meet the team, and see if it's a fit. And if you were building a multi-agent system for trading, you typically have 3 specialized roles. The signal agent, which continuously ingests market data, price feeds, news, order book depth, macro indicators. It's running pattern recognition, maybe a fine-tuned model looking for alpha, opportunities to trade. Its output is a structured signal. What to trade, which direction, and then with a confidence score attached as well. Then there's the execution agent, which receives the signal and handles the how. This isn't just send order to exchange, it's figuring out how to split a large order into smaller pieces so you don't move the market yourself, choosing between exchange venues in real time, managing partial fills. It's latency obsessed and stateful. It tracks live order state across multiple exchanges simultaneously. And the third is the risk agent. This one's watching both of the others. It maintains a live view of portfolio exposure, leverage ratios, regulatory position limits. It's not reactive, it's preemptive. It should be continuously evaluating if the execution agent fills this current order queue, what does our exposure look like in 500 milliseconds? Now here's where the architecture gets interesting. These agents communicate through a few different mechanisms. There's message queues like Kafka for async signal passing. There are shared state stores like Redis for things that need to be read fast by multiple agents. There's the live order book, current positions, etc. And then there's event streams for triggering downstream agents when something happens. The design question isn't just what each agent does, it's what's the contract between them and what happens when that contract breaks. Because feedback loops are baked into the design, the signal agent is reacting to market data that is partially shaped by what the execution agent is doing. That's not a bug, that's reality. You have to architect around it intentionally or you recreate the flash crash in your own system. So let me make this concrete. 9:32 a.m., earnings report drops. 2 data feeds are giving conflicting reads. One shows a beat, the other is lagging by a few seconds and shows a miss. This is a real problem in a distributed system. Data consistency across feeds is genuinely hard. The signal agent ingests the positive feed first. Confidence, 91%. It publishes a buy signal to the message queue. The execution agent picks it up, starts routing large orders across venues. It's doing its job perfectly. The risk agent fires a check. We're at 80% of our sector limit, flag this. But the message arrives 200 milliseconds late because the queue is backlogged. There was a separate market event firing at the same time, and the queue didn't have priority lanes configured. The execution agent, still acting on the original signal and not yet seeing the risk flag, pushes past the position limit. Now you have an overexposed position, a lagging risk layer, and an execution agent that technically executed its task correctly. This is the core architectural lesson. Individual agent correctness does not guarantee collective system safety. The agents weren't buggy. The coordination layer had no enforcement mechanism, just advisory messages on a shared queue. The risk agent could recommend a halt. It couldn't cause one. That's a design choice, and a bad one. So how do you actually build these systems to be robust? A few principles matter. So first, coordination contracts, not conventions. Schema validate every signal before it can be consumed by the execution agent. Define what a valid, actionable system looks like. Required fields, confidence thresholds, timestamp freshness windows. Make it enforced at the infrastructure level, not a gentleman's agreement between services. The execution agent should be incapable of acting on a malformed or stale signal. Second, veto power with latency guarantees, and this is a big one. Your risk agent is useless if it's advisory. It needs to be in the critical path of execution, not listening to a secondary queue. One pattern that works: the execution agent doesn't route a single order until it's received a signed clearance token from the risk agent with a TTL. That token expires in, say, 50 milliseconds. If the risk agent goes down or is slow, execution halts automatically. And this makes the risk boundary a first-class architectural constraint, not an afterthought. Full observability, trace interactions, not just outputs. In a single service app, logging individual functions is enough. In a multi-agent system, you need causal tracing across agents. When something goes wrong, you need to reconstruct. What event triggered what message? Which agent consumed it when? And what state each agent was holding at that moment? Tools like OpenTelemetry with distributed tracing combined with event sourcing on your message broker give you that audit trail. And without it, your post-incident analysis is basically archaeology. Finally, chaos testing before the market does it for you. Simulate agent failure mid-workflow. What happens if the risk agent goes down while execution is mid-fill? What if the signal agent publishes a message with a malformed schema? What if two agents read conflicting state from Redis in the same millisecond? These aren't edge cases, they're scheduled events in a production system, so run them in staging on purpose. So building systems like this well requires a specific combination of skills: strong backend and distributed systems foundations, fluency with how AI agents are actually orchestrated, not just the model layer, but the coordination layer, and the ability to apply both within real domain constraints where failure has consequences. That's what Interview Kickstart's agentic program is designed around. It's a 14-week program taught by FANG instructors, and the finance-oriented capstone I told you about is where you build a multi-agent system dealing with exactly the kinds of design challenges that we talked about today. Coordination contracts, veto enforcement, observability, failure modes. If you want to go from I understand agents conceptually to I've shipped one that holds up under pressure, the link is in the description. And if you've hit a multi-agent coordination failure in production, finance, payments, whatever, drop it in the comments. Those war stories are worth more than any textbook. So thanks for watching and see you in the next one.